CD first, AC. So what is the difference? Which one will be better? Same problem as the breaking the egg. We cannot say this one is better than this one in general. But depending on the architecture of your processor. And also depending on your this one is always the problem of not only hardware but also your compiler, binary code. So if you are using the ultra editor for the executor file or the compiled file, you can see a bunch of such a number. But sometimes you need to decode this one into the real number. But at the time, if you do not know which one is a big endian, which one is a little endian, which one is used in your compiler, you don't understand. Okay, it's really frequently happen, the common problem. But for example, IBM used I think the big endian, but the Motorola they use this one, and Java sometimes they use the mixed one. So benefit of the big endian is the same as you are thinking. So we usually start from the most significant part of the number. So from the beginning and so on. So this is the thing. Okay. Then why we consider the little endian? For example, a lot of if you are using the 64-bit and you are using only the 1 or 2-bit, that's true. So 0, 0, 0, 0, 0, 0, 1, 1, or the 0, 1, 1, 0, 1, 1, 1. You need to read all of this, the 0 part. It's way slow. So a lot of time, your information is in the least significant part. So we can go back than this. And also, think about the data structure in computer science and the mathematics. So usually we start from the least significant part or the inside, the not important one. So for example, y equal ax plus b and the square and something the d, and if this is the parenthesis again. So you need to start from the inside. That inside usually represents the here. So if you remember the CS11 or 102, I think there is 102, the basic data structure class. So when you implement something, such an operation, we can use the step. Why? Because the step put inside, and from the outside, we can calculate. So such a thing, sometimes in terms of performance, a little endian is better. So no matter what method you use, if we know the address, so of this one we can read and this. Okay? Then problem is we are not going to touch the CPU more. So you should learn in your computer architecture class or the microprocessor class or the embedded system or circuit class in your engineering. But this part, not the electrical circuit, but the problem is this one is usually not so big. It's limited by the address because it's nothing but the sequence of address. So we do not have the enough space to keep the whole of this. And also this one is the space, size is one problem. And this one is used for in between. Okay? So if we do not manage it properly, this one, you cannot get the full benefit of the higher the speed device. So in this class, we are going to, in this chapter, we are going to see how to manage and how to allocate, how to use such the memory device. Okay? Any question overall? So please read your old textbook. That will be much, much helpful to understand the many of the chapter in the operating system, and also fun after you understand such a hardware part. Okay, so this is the one of the example that I showed, but I don't have to explain the details. But when we process such an instruction, there are different types of the process. So mostly when we get the instruction from the memory to the register in the CPU, that's called the fetch the instruction. You need to first fetch the instruction, then you need to decode. Because they are in the binary code, then decoded by the definition of the based on the CPU architecture. And sometimes we need to replace the something operand by the value. That's called the fetch operand. So for example, in case of the bx comma cx, sometimes bx can be the address. Then the address should be used. So that is the fetch the operand. Then finally execute that instruction by the CPU. Then result should be saved temporarily in the register. Then get back to the memory. Okay, to keep. Or if you do not have the the fetch operand, then the fetch the operand, then just decode and like the plus, minus, and so on. So then finally we are going to discuss about the memory part. So this is I think the very high level schematic diagram to explain about the definition of the process we use a lot. So this is the memory. Sometimes lower address to the higher address. Sometimes I can use the lower bottom to up. It doesn't matter. Then in this case from the top. So usually lower address is used for operating system. If you take a look at the task manager or the resource monitoring, the first part usually is your operating system or system, something like that. And is used by the operating system. It's kernel. Then followed by the number of process. The problem is, if we go back the characteristic of the memory is nothing but it's a sequential address, which means if you know the address or for example, this is the AAAA, but accidentally this one is changed to BAA, something the electric short or something problem accidentally, then if you go to the BAAA, then you are able to read the data where the BAAA, which is wrong place, but you are able to. Because memory itself is not protected. If you know the address, then go to that the electrical circuit and read the data and send back to the CPU. Okay? Whether or not this is very important process. Whether this is just the garbage data, whether this is operating system, this is other process, it doesn't matter. Okay? There's no security. Okay? So if you know the address, you are able to access the data. So because of that, one of the first important thing when you are using the memory, you need to protect each process. You need to protect each the data structure, like the process, the one. This one is used from the 256K to the 300, the 040 address, only this area. But accidentally, the current CPU know the address of this one, it will be the problem. So we need to protect for each process. So idea is, it's a very simple idea. So to protect, so protection in the memory is mostly the important and first job you need to understand. So to protect, we are going to use the very basic. What is the starting and what is the size of the process, which is called the base and limit. Then this information is in the where? Register. So whenever you have the context switch and it has a base and the limit for each process. So process 0, the base is 256000 and the limit is the size. Size is the difference. Then, for example, in this case, I think the 50,000. 50,000 is the limit, it's the size. Then, this information will be used by hardware. Is the inside the CPU. That is the hardware. This is not the programming, software programming. This is the hardware, the implementation in the CPU. So CPU always check whether base address, the program counter, current program counter is bigger than base. Base is here for each process, and the less than base plus limit. This is hardware the implementation in your the CPU. So CPU check whether this is bigger than the current program counter. PC is bigger than base and less than the base plus limit. So inside the boundary. If this is not in, then it will call the interrupt signal. Something wrong. Okay? This is the out of the boundary, or this is called the threat. Then the operating system do something, the error and stop the current process or the other thing. Otherwise, if that passes to the check, then the finally access the memory with that program counter address. So this is the current idea. But still, there is no clear boundary, or there is no protection physically. So you need to use this base and limit. So memory, a lot of hacking happen in the memory. So because if you are able to access the data in the memory, then the current running process, you can get such information. Okay, so then at that time, some of the, if you are using the only static, the instruction, static instruction means it's not changes, just the static value, 1 plus 2, 2 plus 1, and so on. There might be no problem. However, a lot of time, we don't know whether this process is always here, whether this process is always here. So some of the data is dynamically changed. So that is called the address binding. So address binding means depending on where the process is located, whether current process is here or here, the physical address will be changed. So there are different types of the binding. The first one is compiling time. Compiling time means when you compile, the physical address will be bind, which means it's a setup. That means you need to always load the process in always the same position. For example, MS-DOS. MS-DOS use old operating system. The MS-DOS use only one process at a time. Okay, from the beginning, always. So their physical address is always the same. Okay. However, if you think about I'm going to use 1, 2, 3, 4, 5, 6, 7. 7 seed as the group, segment, as a group. So he is always number 1. 0, 1, 2, 3. So she is always number 3. Okay? So if this team used only this area, we can fix. We can have the static value of the location. However, if they can be the seed, this team in the low, so if I'm using only the 1 and 3, it will not be matched. Okay? So if you bind the address during the compiling time, it's always here. Okay? But if you bind the load time, by the way, what is the difference between the load and the execution? What's the difference? So when you compile, what happens? First, if you compile your source code, it will create object file. It's not executable file directly. Some simple program you can, but most of right now the program language, Java, anything. So when you compile your own source like a hello world, you do not have the string. You should import other thing. Okay? So at that time, if you during the first when you are done for the compiling, you will get the object module only. To execute, to run your object module, you need to combine several other modules, which is already object file. So sometimes you can create the A.object file, B.object file, C.object file. Then by combining these 3 object files, you can have your final executable file. That is called the load. Okay, you can use the link, the command, during the compiling. So this is called the loading time. Load. Then also sometimes so I have the a.out file by combining 3 object files. So when you run the a.out file, a.out file use something library, shared library like the printf, which is not in your the source code, which is not in your the executable file, but while you are running, executing, you will access such a existing library where it's in the memory. Okay, if you remember the shared library that we discussed in the process, so we can access such a shared. So that is called the execution time, run time. So there are 3 different types of that. So if you combine, create the location of the memory address during the load time, this is the load time. However, if you dynamically access while you are running, that is for the during the execution time, you can find the location, address of the file. So that is the binding, the address instruction. In the instruction are the 3 different state. Okay, so what about this one, compiling time? General purpose operating system has not used because we have many processes, sometimes in and out, so definitely not. However, some embedded system, specific purpose of the embedded system, operating system uses such a compiling time. Load time and execution time are used a lot in the general purpose of the operating system. Okay, so this is the step. So there are different. From our side, we have the 3 different address. So this is a physical address, the memory address. Okay, to get this one, first, how do you define the address of your variable? You don't know where it goes. Instead, we are using symbolic address like the integer I or the double J and the float K, like that. So when you define this kind of variable, what happened during the compiling? During the compiling, you need to allocate the 4 byte for the integer I in your memory. So it will be used for the memory, but instruction, you need to use the 4 byte of the data. At that time, location of this data, we don't know exactly where it goes, integer I. Instead, you can define in the process. This process will be exactly copied to the memory space. So let's say this is a 0, 0, 0, and the integer I is the 0f, 0f. So it's the relative, the offset value. So this is called the logical address. So after compiling, it will create the logical address. In other words, it's called the offset from the 10 byte or the F0F byte from the beginning. Then once this one is loaded into the memory, then finally it will have the physical address. So different types of the address will be used. Operating system should take care of such the address, the binding. So logical address is such a relative, the offset. On the other hand, the physical address is finally the memory address you can access. Then, since each process has like the 0, 0, 0, and this is the FFF, and the process 0 and process 1. Process 0, we don't know where it goes. For example, this is a process 0, and the process 1 can be here. So even though it has the same logical address, like 100, 100. This 100 and this 100 are different physical address, right? So we need to know exactly where, because CPU use only the physical address in their program counter and the program counter. So instead, the logical address which means we need to manage logical address versus real physical address. So he is always in the position 1, but position 1 can be different from depending on which law he is in. Okay? So we need to map. So that mapping is called the memory management unit, MMU. It's nothing but just a simple table. So logical address 500 is the physical address, the 220,000. Okay? So this is a relative value for each process. So like for example, 100 of the process 0, 100 of process 0 may be the physical address, like this one is the 1000. So it's the 1100 address. This one is 100. 100 is the 100. It's starting from the 00. So which means we need to map the process 0, the 100 is the 100. 1100. Process 1 is 100 is the 0100, like this one. So this is called the mapping table, memory management unit. Then whenever your process need to access a CPU access the specific location, the CPU take a look at this mapping table first to find the physical address from the logical address, using the logical address and the physical address. Question. Basically, what is this MMU?
Data structure.
It's a data structure to manage the logical address and physical address, which means every time when you access the data to the memory, you need to find this information, look up this information. How often? It's a frequently accessed or the rarely accessed? Very, very frequently accessed. So where is the best place to put this one?
Cache.
So this one is in the first, the memory. Okay. So in the memory, then we can do later we will see how to the speed up. Okay. Even the accessing the memory is not fast enough, so we will use the other approach. But basically, this will be in somewhere in your memory, which means your CPU should know where this table is, right? To find the physical address, first go to the memory of this MMU, then read the data and the physical address, finally go to the memory. Okay? So this table will be managed in where is that? There is I think this one is not here. Later we will see such a name of the table. So this one is the relocation register. This one is called the relocation register. If you go back to this one, there are different types of the register, specific purpose of the register. So relocation register is one of the specific purpose, the register. So depending on the CPU, there are sometimes many relocation register. So relocation register 0, 1, 2, 3. This relocation register will be used for such a memory management unit. So that has the location of the MMU. Then the CPU read the data, then finally find the address, and using the physical address, access the data and load into the CPU. So that is how it works. Okay. So this relocation, the register, the MMU is the same idea as the base and the limit. Okay. The base and limit is just to check the starting and the ending, but this one, check where is the physical address, then using the physical address and finally access the data. Okay. I already explained about the dynamic loading. Dynamic loading is the tool, like the DLL file or the shared library. So everybody use the shared library like the standard input and output, STDIO. Then we don't have to put the same code on the memory, okay? Instead just one, then the dynamically accessed by the many processors, the shared library. That is called the dynamic loading. The main purpose of always the memory management is the reduce the utilization, okay? Because if we use the maximum like the 100% of the memory, we need to do additional operation to make the space. So try to minimize the space, so like the dynamic loading. And also speed. So we will use the dynamic approach, dynamic linking. There are two types of the dynamic linking. One, actually the static linking. Static linking is even though if we are use the shared library, it will be accessed by the many processors slightly slower, okay? Instead of using your own library. So when you compile, if you don't want to use the shared library, dynamic linking and dynamic loading, you can compile with the static, the compiler. So one time, when we upgrade the system, it was I think the DEC Alpha system from the 32-bit to the 64-bit, the processor. So they said, the company said that we don't have to change anything, just recompile all the code, okay? Then run it again, then there might be no problem. However, when we recompile and run, there's always error. So we realized that shared library is not actually compiled properly. So to address that problem at the time, we compile all the program using the static, the linking, okay, static library, then it run properly without any error. Problem? Each process size is huge because it keeps all the copy of the library, then the process size will be huge. Okay, so you can think about such an alternative way. In case you encounter something, the problem of the shared library, you can compile with the static library, okay, instead of dynamic. But eventually you need to address that. Okay, after you address the problem, you can use the shared library. Okay, so we try to our best to save the space of the memory. What if we use all the space of the memory? We need to free up. If all the space, the seat are taken, but there are the other people, so we need to make the free space. Those who are sleeping in this classroom, kick out of that, then give the chance to the other student. So that will be happen in the memory management, which is called the swap in and out. So what does that mean, swap? Like the wife swap. Is it still going on, the TV show? I'm not sure. It was, I don't watch the TV a lot. So there was a TV show, like the wife swap. So you can change the wife, then not sure whether that is the best or not. Anyway, so we can swap the process by process. If all the space are used, we can remove. Actually, not remove the backup to the storage. Is one of the process. Then the load the new process into it. This is called the swap out. This is called the swap in. It was used before, but nowadays not. One main reason. First, what happened when you swap out, swap in? I/O, transfer, I/O, transfer, I/O. It takes a long time comparing to other speed. So, and also nowadays, memory size is bigger and bigger. So if you check your resource monitoring, the mine is usually 70 to 80%. of the utilization of the memory. Still, I have the space. So since we have the pretty much relatively the enough space to run the process, so we do not use the swap in and out. However, if you see your operating system like the Linux or the even Windows, still you can see the swap, okay, like I mentioned here. So nowadays the swap means it's a virtual memory. So even Windows, it's not critically the important functionality, but still it has the function to change the size of the virtual memory. And also, if you see your Linux or Unix machine, there's a swap space still. That's also used for the virtual memory. Virtual memory, as name implies, it's not real memory, but we consider it a virtual memory. We will see in the next chapter, chapter 9. So, swap in and out is the way to free up the space, but nowadays it's not practically used. But still, name of swap is used in the virtual memory. We will see details of virtual memory later. So swap in and out. Okay. And I'm going to, you can quickly check how long it takes. Okay. So it's based on the I/O overhead and latency and transfer rate. It takes a long time. So, okay. What about the mobile system? Definitely, mobile system like your cell phone will not use the swap because it takes a long time. However, one of the main problem of the mobile device is the limited hardware specification, like the memory size not bigger than the personal computer or other server. So because of that, actually first, the Android, iOS, they didn't allow multitasking. Multitasking means what? A number of processes are running concurrently, same time. Then just using the graphical user interface or other interface, you can switch quickly. Still, they're running concurrently, which means more memory. And also, not only just the memory space, but consume energy. The battery is still limited. So to address that, actually, they block the multitasking. However, nowadays, more and more, the current operating system, mobile operating system, allow multitasking. I just update my iOS for the iPad. I'm using only iPad for the Apple device. So it allows multitasking. It's not like your PC, but it's you can multitasking to application. Okay, and also voluntarily. The voluntarily means so you can actually stop. Okay, your application by the user to free up the space. But probably it's not only the problem of the hardware specification on the cell phone device, but energy, battery power, is the critical. So to save the critical the battery power, they are not supporting the full service as like your PC, but it's also okay. So next issue is so when we have such the memory space, eventually your operating system, when the user start your program from here, you need to allocate, make the space for the program. That is called the allocation problem. So allocation idea, if we can find the free